gate turn off thyristors, that is GTO. A gate turn off thyristor is PNPN device that can be turned on like an ordinary SCR, that is silicon control rectifier, by positive gate current pulse and can be turned off by negative gate current pulse. So just by controlling the gate current, we can easily turn on and turn off the device. Figure A shows the structure of gate turn off thyristors, and figure B shows a symbol to be represented for GTO. The prime objective of GTO, that is gate turn off thyristor, is to achieve fast turn off time and high current turn off capability to enhance the safe operating area. With negative gate current in true in two transistor analogy, the PNPN transistor's collector current is diverted away from the base of NPN transistor, and this NPN transistor is turned off. So the collector current falls and thus PNP transistor is also turned off. Finally, the entire device, that is PNPN layer, is turned off. But during such turn off in ordinary structures, the negative gate current causes electron hole plasma concentrated at the junction that results in high current density, which will not only slows down the turn off process but can lead to device failure due to second breakdown. The prime objective of GTO is to increase the turn off time, or the time should be fast enough to turn off the device. But by this method, that is, first of all, we need to divert the current from PNP and NPN transistor. Thus, first of all, we need to turn off NPN transistor, then turn off PNP transistor. So we have two transistors, NPN and PNP. So first NPN transistor is turned off. After that, the collector current will fall down, due to which PNP transistor will turn off secondly, and after that the entire device having PNPN will be turned off. But while doing this, so due to a negative gate current, there is a electron hole concentrated at the junction of the device. This results into higher current density, and if the density of current increases, it slows down the turn off process of the device. Not only it slows down the turn off process, but also may result into failure due to breakdown. Now, in this gate turn off thyristor, we are going to study two types of characteristics. First, VI characteristic, and second, switching characteristics. So, let us concentrate on VI characteristics of GTO. The figure shows the VI characteristics of GTO. When gate current is not able to turn on the GTO, prior to turn on, the GTO behaves like a high voltage low gain transistor. After turn on, GTO is latched into conduction and behaves like SCR. So once the GTO is turned on, the characteristic is similar to that of silicon controlled rectifier, that is, it goes into forward conduction mode and it gets latched down, and when it gets latched down, the current flowing in the output terminals increases to a large value, that is, it goes into a latching mode. The holding and latching current are much higher than those of conventional SCR. So if we compare the magnitude of holding and latching current of GTO with respect to silicon controlled rectifier, that is SCR, the magnitudes of holding and latching current are much higher than SCR. Now, switching characteristics. The gating requirements of GTO includes injection of current into gate for turn on, and second, application of negative voltage across gate cathode, which must be less than gate cathode reverse breakdown voltage but high enough to extract the charges from P base. So here is the switching characteristics of GTO. The turn off characteristics of GTO is as shown in figure. The total turn off time denoted by TQ consists of three intervals, namely storage time TS, fall time TF, and tail time TT. So the total turn off time is equal to addition of all these three intervals, that is TQ is equal to TS plus TF plus TT. The storage period begins with flow of negative current. During storage time, excess holes in P base are taken out by negative gate current and the center junction becomes out of saturation. Thus, GTO is prepared for turning off. Anode current and anode voltage in storage time remains constant. But as soon as the storage time is ended, that is after TS, the anode current begins to fall rapidly and anode voltage starts to increase rapidly. The fall time is measured from the instant the gate current is maximum negative to the instant anode current falls to its tail current level. During fall time, the anode current falls more rapidly. At the end of fall time, that is TF, there is a spike in voltage due to abrupt current change. That is, instantly the current gets changed, due to which there is a spike in a voltage after the end of fall time TF. After TF, the anode current changes slowly, and this portion is called the tail current, and the interval, that is time interval, is called as tail time, denoted by TF. That is, sorry, it is denoted by TT. At the end of TF, anode current reaches to zero value and the anode voltage undergoes transient oscillation due to snubber circuit components and then stabilizes to its off state value, that is VAK. So if we consider the total time or the total off time in of the switching characteristics of GTO, it consists of three intervals, that is storage time, fall time, and tail time. In storage time, the anode voltage and current remains constant. In fault time, the current falls down and the voltage increases rapidly. And at the end of fault time, then there is a spike in the voltage due to the abrupt current, and at the end the anode current reaches to zero and the anode voltage goes to its transient oscillation due to snugger circuit components and then stabilizes to its off state, that to a value called as VAK. So this is about the switching characteristics of gate turn off thyristor.